Okay, give me a second. This is it. Muito boa tarde, bem-vindos a todos ao colóquio dessa sexta-feira. E eu vou apresentar o palestrante de hoje. It's my pleasure to introduce to you this afternoon, the speaker of this afternoon, Professor Steven Weintraub. I met Professor Weintraub due to our duties in AMS, and he is a professor at the Lehigh University in Bethlehem, Pennsylvania. And his main area of interest is algebra. And he has written over 70 scientific papers and also books, and is a very experienced researcher in his area. And he's going to deliver a talk this afternoon in our colloquium. Unfortunately, I cannot see his slides. I've just found the title. Sorry for that. He's going to talk on periodicity of generalized continued fractions. Thank you very much, Steve, for accepting our invitation. It's a pleasure to have you here, and the floor is yours.
Okay, thank you very much for the invitation. I'm glad to be here there, if only virtually. I'm talking to you from my office in Pennsylvania. If you look outside there's my window. You can see it's late fall here. There's a huge tree out here, but as I say, we're in the northern hemisphere, so this tree has just lost its leaves. But now let's go to the mathematics, and let me bring up my slides, and we will begin.
Okay, you're ready to go.
Right. Okay. I'm sorry. Let's get it. We're read mode again. All right. So what I would like to talk about is periodicity of generalized continued fractions. Generalized continued fractions have been studied since at least the 18th century. If not, I'm not an expert on the history, but they go at least that old. But I'm going to tell you some 21st century results. And I first began investigating continued fractions with a student of mine named Max Anselm. We wanted to look at a generalization of the classical theory where the numerator 1 is replaced by an arbitrary positive integer n. Of course, I'll explain to you what all these means. And we want to look at the question of periodicity of the best continued fraction expansion with numerator n of the square root of e for a non-square positive integer. So again, I'll have to explain to you what all of these things mean, and I will. Okay, so let me begin by telling you about the classical theory of continued fractions. And first of all, I'll tell you what a continued fraction is. Okay, so I'm going to consider classical continued fractions. I'm going to call them CF1 expansions. So continued fraction is CF and 1. And here's a continued fraction. It's an expression from A0 plus 1 over A1 plus 1 over A2 plus 1 over A3, etc., where A0 is a non-negative integer and A1, A2, A3, etc. are positive integers. And the standard notation for this is bracket A0, A1, A2, A3, etc., close bracket. So I'm going to adopt that notation, except that I'm also going to put a sub 1 here because these ones here, these are the numerators, these are all 1. So this is the classical theory where you have the numerator 1. Okay, so let me tell you how to find the continued fraction expansion of any positive real number. Okay, so it's the following algorithm. We start with some positive number x0, we start with I equals 0, and at any stage, we choose a sub I to be an integer between x sub I and x sub I minus 1. So we notice that if x0, or if x sub I is not an integer, there's going to be some unique such a sub I. If x sub I happens to be an integer, then we could choose either a sub I to be x sub I or x sub I minus 1. But in any case, we make this choice, we let Ri be the remainder, and if Ri is equal to 0, we're finished. Otherwise, we let x sub I plus 1 be 1 over r sub I, we increment I, and we loop around. So this is a procedure here. I'll do an example in a minute or two, but let me make some more general remarks. So if this procedure actually terminates, this is some finite expression here, and x0 is the value of this expression, a0 plus 1 over a1 plus 1 over a2 plus 1 over a3, etc. If it doesn't terminate, we could always write x0 to be this expression formally, but it's not just a formal expression. We can look at what are called the end convergence. We chop off the sequence at stage n and stop there, and that gives me some well-defined rational number, in fact, and x of 0 is the limit of this sequence. So x of 0 is equal to this. In this sense, is actually the limit of these finite convergence. We also should notice, as I mentioned, that the choice here is unique, except if x of I happens to be an integer, in which case we could choose a sub n to be either x sub n or x sub n minus 1. So if a sub n is x sub n, we're finished. If a sub n is x sub n minus 1, then r sub n is equal to 1. So x sub n plus 1 is equal to 1, and then we have to choose 1 here. So this is the only ambiguity in a classical continued fraction. And we should also notice that this condition is exactly what we need to continue, because this says that r sub I is less than or equal to 1. That says that x sub I plus 1 is greater than or equal to 1. And of course, we're always looking for a sub I to be a positive integer. So x sub I greater than or equal to 1 guarantees us that we can find a sub I to be a positive integer. Rather, a sub I plus 1 to be a positive integer. And also, we want to notice one more thing here, that x sub I is a sub I plus r sub I. And from this we get that that r sub I is 1 over x sub I plus 1. So we see that x naught can also be written as a0 plus 1 over x1, or a0 plus 1 over a1 plus 1 over x2, etc. So to illustrate this procedure, let's look at the square root of 19, and let's find the classical continued fraction expansion of the square root of 19. Why did I choose 19? Well, it turns out to be an excellent example, but the reason I chose it is that Legendre wrote this great textbook on number theory, and he chose the square root of 19 to illustrate a continued fraction expansion. So I figured if it's good enough for Legendre, it's good enough for me. Okay, so here it is. We look at the greatest integer in the square root of 19, which is 4. Okay, the remainder is going to be square root of 19 minus 4, or minus 4 plus the square root of 19. x1 is 1 over r0. It's the reciprocal of this. And then we rationalize the denominator. We multiply by the, we have 1 over minus 4 plus the square root of 19. We multiply by minus 4 minus the square root of 19 over itself. And a little manipulation shows that this answer is 4 plus the square root of 19 over 3. Okay. You look at this number is between 2 and 3. So the greatest integer is 2. The remainder is this minus 2. x2 is 1 over the remainder. A little algebra shows that this is 2 plus the square root of 19 over 5. The greatest integer in this is 1. Here's the remainder. X sub 3 is 1 over the remainder. That's 3 plus the square root of 19 over 2. So we just continue in this fashion, and let's see what we get. Well, I said that x0 is a0 x1. So here's 4, and then 4 plus square root of 19 over 3. The next stage, it would be 4, 2, and 2 plus square root of 19 over 5. The next stage would be 4, 2, 1, 3 plus the square root of 19 over 2. And we just continue in this way. And when you continue in this way and you get down to x sub 7, you will find that x sub 7 is 4 plus the square root of 19 over 3. That's equal to x sub 1. So the continued fraction will repeat from here, right? What happens at any stage only depends on x sub I. That tells you what happens at the next stage. So whatever started from here is going to repeat from here. So the continued fraction is going to look like 4, 2, 1, 3, 1, 2, 8, and then it's going to be 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8, etc., repeating forever. So we adopt the standard notation. We put a bar over this. So 4 and 2, 1, 3, 1, 2, 8 means 4, and then 2, 1, 3, 1, 2, 8, repeating forever. And we call this periodic, right? It's periodic with period 6, where by periodic we mean eventually periodic, right? The period doesn't start with 4, it starts with 2, but starting with 2, it's periodic of period 6. Okay? So now let's look at some general results about continued fraction expansions. First of all, if x0 is not a rational number, then x0 has a unique expansion, because if x0 is not a rational number, then none of the x sub i's will ever be an integer, so the value of a sub I is forced, and we get a unique expansion. Okay? If x sub I is is a rational number, then, if x0 is a rational number, it's going to have exactly 2 expansions, and that comes from this ambiguity that I said at the end. We can either choose a sub n to be equal to x sub n, or x sub n minus 1, in which case we continue one more stage and we get a 1. And then we have the following theorem, which says that a positive real number has a finite expansion if and only if it's rational, and it has a periodic expansion if and only if it is a classical expansion, right? Continued fraction with numerator 1. I want to emphasize that in the classical case, numerator 1, we have a finite expansion if and only if the number is rational, and a periodic expansion if and only if it's a quadratic irrationality. And here, as I said, periodic means eventually periodic from some point on. And 3/4 of this theorem is very straightforward. 1/4 of this theorem is a real theorem. The implication that x0 is a quadratic irrationality implies that its classical continued fraction expansion is periodic. That's a real theorem, and that's due to Lagrange. It's an 18th century theorem of Lagrange. Okay, now I said this works for any positive real number, and in fact, for any quadratic irrationality, we're going to have a periodic expansion, classical expansion with numerator 1. But instead of looking at an arbitrary quadratic irrationality, let's look at a particular one. Suppose we look at a non-square positive integer. So the square root of e, that's a quadratic irrationality. If e is a non-square positive integer, then it lies between 2 perfect squares, right? So let's let e lie between d squared and d plus 1 squared. It has a periodic expansion, let's call the period k, and then the expansion has a very particular form. It looks like it's periodic beginning with a1, a0 is d, the end of the period is 2d, and the first k minus 1 elements in the period form a palindromic sequence. So what is a palindromic sequence? It's a sequence that reads the same left to right as it does right to left. So if we look at our example of the square root of 19, here we have it. We have a period of 6. Here's d, here's 2d. And if you look at the first 5 entries here, everything in the period except for the last one, it's 2, 1, 3, 1, 2 from left to right, and it's also 2, 1, 3, 1, 2 from right to left. So the continued fraction expansion, the classical expansion of the square root of e, has this very particular form. Okay, now there are very many reasons for being interested in continued fractions. As I said, people have been thinking about them for well over 200 years. And here's one of the reasons for thinking about them. It has to do with the relation to solution of Pell's equation. So people thought about Pell's equation even earlier. Fermat thought about Pell's equation. Pell's equation is the equation x squared minus e times y squared equals 1. And it's certainly not obvious if you take some number e, which is not a perfect square. It's not obvious whether this has any solutions at all, but in fact, x squared minus e times y squared equals 1 always does have solutions, in fact, infinitely many solutions, and we get them from continued fractions. So let's see how to do that. First of all, let's again be a little more general before we get to this here. Let's take any positive real number and look at its continued fraction expansion. We can define 2 sequences of integers inductively as follows. We let p sub minus 2 equals 0, p sub minus 1 equals 1, and then we define p sub n inductively as a sub n, p sub n minus 1 plus p sub n minus 2, where we're taking the a's from the expansion of x sub 0, and a similar sort of expansion for the q's, except we have a different starting values, but a similar recursion. Q sub n is a sub n, q sub n minus 1 plus q sub n minus 2. And if you let c sub n be the quotient p sub n over q sub n for n at least 0, then c sub n really is the nth convergent here. If we take this infinite continued fraction and we chop it off at a sub n and we look at the value c sub n of this continued fraction, finite continued fraction, then c sub n really is p sub n over q sub n. Okay, and that works for any x sub 0. Okay, now let's return to thinking about the square root of e. And if we think about the square root of e, let's look at the following number, p sub n squared minus e times q sub n squared, for n at least minus 1. So in order that n is equal to minus 1, we're looking at p sub minus 1 squared. That's 1 squared minus e times 0 squared, so that's equal to 1. Okay. And now we will make we'll do some language. You know what it means for something to be periodic? Periodic means that it repeats. Well, we're going to say that a sequence is F periodic if it repeats up to a factor of F. So a sequence is F periodic at period J starting from n equals m if when we take d sub n plus j, it's not equal to d sub n, but is d sub n times the factor F for all n greater than or equal to m. And then we have the following theorem from the theory of classical continued fractions. We know this guy is periodic. Suppose the period is k, then these numbers w sub n are minus 1 to the k, periodic of period k, starting at n equals minus 1. So for simplicity, let's think about the case when k is even. Of course, minus 1 to the k for k even is just 1 periodic or periodic. So in the case k is even, the w sub n's are periodic of period k. So what does that mean? It means that w sub minus 1 is equal to 1. It means that w add k to it, w sub k minus 1 is equal to 1, w sub 2k minus 1 is equal to 1, w sub 3k minus 1 is equal to 1. In fact, w sub mk minus 1 is equal to 1 for any integer m. And what is w sub mk minus 1? Well, it's p sub, or I wrote it as km, p sub km minus 1 squared minus e times q sub km minus 1 squared. So I see that p sub km minus 1 squared minus e times q sub k minus 1 squared is equal to 1. In other words, I get a solution of Pell's equation, x squared minus ey squared equals 1. And in fact, I get infinitely many solutions because I just look at any multiple of the period. And it's a theorem that says that not only do I get solutions to Pell's equations from non-negative integers in this way, but in fact, we get all solutions to Pell's equation, or even to the equation x squared minus ey squared equals plus or minus 1 in non-negative integers. They all arise in this way. So again, let's look at an example and let's stick with 19, okay? So we said here, if we go back to our expansion of 19, we notice that this expansion here had period 6, right? So the values of n we're going to look at are n equals minus 1, 5, 11, 17, etc. And if you look at these partial quotients, you will find that p sub n and q sub n are as follows. So for n equals minus 1, we get 1 minus 19, 1 squared minus 19 times 0 squared equals 1. Well, that's trivial, but then things start to get non-trivial. We get 170 squared minus 19 times 39 squared is equal to 1. 57799 squared minus 19 times 13260 squared is equal to 1. 19651490 squared minus 19 times 4508361 squared is equal to 1, etc. We get infinitely many solutions to Pell's equation, and I just wrote a bunch out. Numbers get big, but it's really true that this huge number squared minus 19 times this huge number squared is equal to 1. Okay, so that's what I wanted to tell you about classical expansions. And now what we're interested in is what we're calling CFN expansions. So CFN means continued fraction numerator n, but now we're going to replace the numerator of 1 by a numerator of n. So we're going to say that the CFN expansion is something that looks like a0 plus n over a1 plus n over a2 plus n over a3, etc., where, again, we have numerators n here. All of them are n rather than 1. And again, a0 is arbitrary integer, or non-negative integer, and a1, a2, a3, etc. are all positive integers. Okay? And the theory sort of starts off the same way. First of all, there's an algorithm for getting these generalized guys, and here is what it is. Again, we start with I equals 0, and in any stage, we choose a sub I between x sub I and x sub I minus n, like minus big N here. So we notice here that as opposed to the n equals 1 case where we would get usually 1 choice and sometimes 2, here we're always going to get exactly n choices if x sub I is not an integer, and otherwise we'll get n plus 1 choices if it happens to be an integer. But so we can always make this choice here. We let r sub I be x sub I minus a sub I. Once again, if r sub I is equal to 0, we're finished. Otherwise, we let x sub I plus 1 be n over r sub I. We increment I, go back to here, and loop. And so things start off being the same. X0 is equal to this a0, a1, a2 up to a sub little n. If this terminates at stage little n, otherwise we can write x0 to be this formal expression. And once again, it's not only formal, it's in fact the limit of the finite convergence. Second, we observe that this condition is exactly what we need to continue once again, because this says that the remainder is less than or equal to capital N. So if x of I is x of I plus 1, rather, is capital N over the remainder, x of I plus 1 is greater than or equal to 1. So we can choose a sub I plus 1 to be a positive integer. And once again, we get the same sort of thing here, that x sub I is a sub I plus r sub I, which is capital N over x sub I plus 1. So x0 is a0, x1, so capital N is a0, a1, x2, sub capital N, etc. Now, I mentioned that we always have more than one choice in case capital N is bigger than 1, but at each stage, we could try to make the closest numerical approximation to x sub I. So in order to get the closest numerical approximation to x sub I, we would choose a sub I to be as close to x sub I as possible. So we think of that as the best choice, which gives us the best numerical approximation. Of course, this is now unique, right? We're choosing x sub I to be the greatest integer, so we have a unique best continued fraction expansion, and I'm going to call the best continued fraction expansion, I'm going to give it some notation. I'm going to put double brackets for the best one. Okay, so this is, so any continued, any positive real number has a unique best continued fraction expansion with numerator n. So to illustrate this, let's try to look at the at 19 again, and let's look at the best continued fraction expansion of the square root of 19 with numerator 2. Okay, so again, a0 is 4. Here's the remainder. Now x1 is 2 over the remainder. It's 2 over minus 4 plus the square root of 19. Okay, little arithmetic shows that this is 8 plus 2 times the square root of 19 over 3. Okay, the greatest integer in that is 5. R1 is this minus 5, which is this. X2 is 2 over R1, which is turns out to be 14 plus 4 times the square root of 19 over 9, and we continue in this way. And if we continue in this way, and here's what we're going to get. Here we'll get 4 and 8 plus 2 times square root of 19 over 3, then 4, 5, 14 plus 4 times square root of 19 over 9. We continue in this way, right? We get all these different numbers here. But now, actually, when we get up to x sub 9 here, x sub 9 is the same as x sub 1. Okay? So you notice that we're going to repeat again. So the continued fraction repeats from here, and what we'll get is we'll get 4, and then 5, 3, 4, 34, 4, 3, 5, 8, and then continuing forever, right? 5, 4, 5, 3, 4, 34, 4, 3, 5, 8, 5, 3, 4, 34, 4, 3, 5, 8, 5, 3, 4, 34, 4, 3, 5, 8. It continues forever. So here's the continued fraction expansion, the best continued fraction expansion of the square root of 19 with numerator 2. And what I want to point out is that this is completely different than the case n equals 1. If you remember, in case n equals, well, we had a 4 here and an 8, but if you remember, in case n equals 1, we had a period of 6, right? So there we had a period of 6, here we had a period of 8. So we had we have a completely different period. And if you look at these numbers here, well, for 1 it was 2, 1, 3, 1, 2, 8. Here these numbers are completely different. So this is a completely new animal. It doesn't come from n equals 1. It's a completely new animal. Okay. So we've gotten a new phenomenon here, a new continued fraction, and now we want to think about these guys in general. Okay, the first thing so we're going to think about these in general. The first thing we're going to think about is, when do we have a best expansion? Well, it's not really useful to say that we have a best expansion is the one given to us by our algorithm. What we would really like to look at is we'd like to look at some CFN expansion and be able to look at this expansion and decide whether it's best. And there's actually turns out to be a very easy criterion. If we look at a terminating expansion, it's best if all of the integers starting with A1 are positive integers that are greater than or equal to capital N, and the last one is greater than or equal to capital N plus 1. And a non-terminating expansion is best if all of the AI starting with A1 are greater than or equal to capital N. And that's actually very easy to see, so let's see it. Suppose a sub I is the greatest integer in x sub I, right? This is exactly what the definition of the best expansion is. Well, that will be true if and only if the remainder here, x sub I minus a sub I, is less than 1. And that will be the case if and only if n over the remainder, which is x sub I plus 1, is greater than n. And that will be the case if and only if the greatest integer in x sub I plus 1, which is a sub I plus 1, is greater than or equal to n. Right? So if we have a best expansion, then the a sub I plus 1 is greater than or equal to n, and vice versa. Okay, so this is our criteria for getting a best expansion. Okay, now I want to put, the next thing I want to tell you is a method for producing expansions, which I'm going to call inflation. It's kind of a cheap method. And here it is, not necessarily best expansions, but expansions. So suppose we start with a CFK expansion, A0, A1, A2, A3, etc. Its n-fold inflation will be the CFNK expansion that I get by leaving all of the even A's alone and multiplying all of the odd A's by capital N. So I sub capital N of A0, A1, A2, A3, etc. sub K is A0, capital N A1, A2, capital N A3, etc. sub capital NK. And the point about inflation is that inflation does not change the value of the continued fraction. If the original continued fraction had value x sub 0, then its inflation also has value x sub 0. And once again, that's something very easy to see, so I'll just show it. Here's my original continued fraction, A0 plus k over A1 plus k over A2, etc. So now I'll use one of the standard tricks in mathematics. I'll multiply by 1. In fact, I'll multiply by 1 in the form capital N over capital N right here. Right over here, right here. When I multiply by capital N over capital N, what happens? Well, I get this k becomes a capital N times k, and what happens here? This A1 becomes a capital N times A1, and this k becomes another capital N times k. So this expansion now looks right like this. The next place I'll multiply by n over n is right over here. So when I multiply by n over n right over here, I'll do the same sort of thing. I will be changing a sub 3 to capital N times A3, but leaving a sub 2 alone. So the next stage, I will be getting A0 plus capital NK over capital NA1 plus capital NK over still A2 plus next stage is capital NK over capital N times A3, etc. So simply by multiplying by n over n at every other stage, I will get this expansion here. And of course, multiplying by n over n doesn't change it. Now, we're interested in the question of periodicity, and I'll simply observe if we have something that's periodic and I multiply every other term by capital N, I wind up with something that's periodic. The period may change. I don't want to, I've written down exactly what the period is, but let's just note here that if the original period is P and I multiply every other entry by capital N, then the new period is going to divide period 2P. Okay? All right, one thing that okay, so let's just keep that in mind. Okay, so I mentioned that inflation is a way of producing periodic expansions, so this enables me to prove the following corollary. Suppose I look at some positive real number x sub 0, then x sub 0 has some finite CFN expansion, that is continued fraction numerator n, if and only if it's rational, and it has some periodic expansion if and only if it's a quadratic irrationality. And again, 3/4 of this is easy to prove. The hard part is to prove that if x0 is a quadratic irrationality, then it has some periodic CF capital N expansion, but we can do that easily. We can just start with the CF1 expansion, which Lagrange's theorem tells us is going to be periodic. That's the hard part. And once we know that that's periodic, well, then it's easy. We just inflate that one and we get a periodic expansion. So the only ingredient is Lagrange, but once we have Lagrange, the rest of this theorem is easy. We just use inflation to get this direction. But the thing we should note is this inflation will not be best if n is large enough, because remember, what do we do in inflation? We leave half of the coefficients alone and we change the other half. And remember that our criterion for being best is that each of these coefficients has to be bigger than capital N, greater than or equal to capital N, right? So once we choose capital N to say be bigger than A2 here, or bigger than wherever the periodicity starts, right? Forget about periodicity, but once we choose capital N to be say bigger than A2, it's not going to be a best expansion. So this will always produce periodic expansions, but it may produce expansions. Inflation may produce periodic expansions for a while, but sooner or later it's going to run out, and we won't get periodic expansions. Okay, so I said that what we're really interested in is best expansions, right? They're the really natural expansions to look at, the best approximation numerically at any stage. And sure enough, it turns out that the best CFN expansion of a rational number is always finite. Okay? And now you might think, oh, well, same thing should be true for quadratic irrationalities, the analog, that is, that the best periodic expansion should always be, the best CFN expansion should always be periodic, but we don't believe that. We conjecture quite the opposite, that it is not always the case that the best CFN expansion of a quadratic irrationality is periodic. There are very many cases where it is, but we conjecture that it's not always true. Why do we conjecture it's not always true? Well, we did a lot of numerical explorations, and we have a lot of numerical evidence. So let me give you two examples here. We did this computation out to 6,000 terms, and the best CF2 expansion of the square root of 124 and the best CF7 expansion of the square root of 8, they're not periodic within their first 6,000 terms. Of course, it doesn't prove they're not periodic. They could always start being periodic with periodicity 7,000, right, bigger than 6,000, but we don't believe it. We believe they're not periodic. And if you think 6,000 isn't good enough evidence, well, some Dutch mathematicians got interested in this, and they looked at the number x of 0, which is -4 plus the square root of 37 over 3. There's nothing magical about x of 0. They simply choose x of 0 to be the number that they looked at the classical expansion, and they chose the number with classical expansion 0, and then 1, 2, 3 periodic of period 3, starting with a sub 1. And they did a much more difficult numerical calculation to show that the best CF2 expansion of this number is not periodic within its first 70,000 terms. So if you didn't think 6,000 terms was good evidence, 70,000 terms looks like pretty good evidence to me, and I hope to you too. So we believe this conjecture, but I must admit we have no idea how to prove it. Okay. All right. Now let's go on and keep this in mind here. Often, as when you investigate something, you find that there is a distinction which wasn't clear a priori, but is clear after your investigation, and that turns out to be the case here as well. So suppose we want to look at the expansions of the square root of e with numerator n, the best expansions, and it turns out there's a distinction to be made. So let's let d be the greatest integer in the square root of e. So e then is a capital D squared plus a with 1 less than or equal to a less than or equal to 2 times capital D. So I'm going to establish this notation that I'm going to use. E is d squared plus a. Then n is small for e, or simply small if e is understood, if n is less than or equal to 2d, and n is large if n is bigger than 2d. And so the classical case, n equals 1 is always small. Okay? And now we have the following theorem. Suppose that the square root of e, the best CFN expansion of the square root of e, is periodic. As I say, we conjecture this is not always the case, but it's the case a lot of the time. Suppose that this has period k. Okay? Then if n is small, the shape of the continued fraction is the same as the shape for n equals 1. Namely, the period is always going to start at a1. The last entry in the period is going to be 2d. And the first k minus 1 entries are palindromic, right? So we had that for the square root of 19 as well. If we looked at the best CF2 expansion of the square root of 19, here we had period 8 here, right? But the first 7 guys are palindromic. 5, 3, 4, 34, 4, 3, 5 reads the same left to right as it does 5, 3, 4, 34, 4, 3, 5 right to left. So if we're looking at the case where capital N is small and we have a periodic expansion, then it's of the same sort of shape here. It's whatever it is, the last guy is 2D and the first k minus 1 guys are palindromic. And the period always starts with A1, just as in the classical case. On the other hand, if n is large, the period doesn't start with A1, but the period always starts with A2. So the period always starts with A2, and you notice I didn't say anything about it being palindromic because it isn't always. It's a good thing we did lots and lots of numerical examples because almost all the time it's palindromic, but it's not true all the time. So there's at least one counterexample, and so we don't have a theorem, right? It's not always the case that it's palindromic. Okay, so let's look at some more examples. Let's go back to the square root of 19, And I told you what the CF1 and CF2 expansion of the square root of 19. Let's look at a bunch of expansions with other numerators, right? So here's the best CF1 expansion, the best CF2 expansion. Before we do this, let's observe that for the square root of 19, capital D is 4, the greatest integer in the square root of 19. So 2D is 8. So numerators that are 8 or less are small, and numerators that start with 9 and are bigger are large. Okay. So here are the ones for 1 and 2. It turns out that the continued fraction expansion with numerator 3 is periodic of period 1, starting at A1. It's 4, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, forever. For 5, it's periodic, again, starting with A1. Period 4 actually turns out to be palindromic here. Okay. For 6, the one for 6, actually, that's a best expansion here, which is the twofold inflation of the best expansion for 3. Okay. So those are all the small cases, and then we start off being large, and the square root of 19, 9, that's going to be periodic starting with A2 here. Period is 2 here. Of course, that's automatically. If this guy only has length 1, then he's certainly the same left to right as right to left. Square root of 19 sub 18, again, that's the twofold inflation of square root of 19, 9, so it's going to be period 2 starting with A2. Square root of 19, 20, that's period 18 starting with A2 equals 2. I just didn't write down all these 18 numbers because they don't fit on the line, but we computed them. Square root of 19, 27, period 2 starting with A2. Square root of 1930 is period 6 starting with A2, etc. Right? In fact, here's another one with 42 is period 2 starting with A2, and then everybody else here turns out to be inflation, either inflation from 9 or inflation from 42. So why did I choose these values of n to write these down? Well, I chose these values of n because our numerical evidence indicates that for exactly these values of n, these are the ones for which, for values of capital N less than or equal to 100, for which we get periodic expansions. Okay, so this was our numerical evidence, and that's where Max and I left it, right? So you'll notice here, as I said, inflation will only produce a best expansion a finite number of times. Sooner or later, we're going to run out. Okay, so we sort of have base cases that aren't inflation, and at this point, we simply didn't know here. It's hard to tell when a numerator gives you something periodic. For example, 5 is periodic and 20 is periodic, but 10 isn't. And almost all the time, these guys here, n's are divisible by little a. Remember, capital N is about E is 19, so E is D squared, which is 4 squared plus 3, so A is 3. So almost all the time these are divisible by 3, but not always, right? So it's really a mystery. There's no formula for telling us when a capital N will give us something periodic, and it's not even clear whether we get finitely many or infinitely many. These sort of base cases here, right? They look like they're getting more rare. So and any base case gives us only finitely many cases from inflation. So the question is, are the base cases going to run out after a while, or are they going to continue forever? Well, so that's where Max and I left it, and then I started thinking about it some more. So let me tell you some more results here, okay? So I'm going to not focus on what the exact expansions are. I'm going to just focus on periodicity. So if you look at this table here and you summarize it, what you see here is that here's the answers for n less than or equal to 99. Okay, so here are the cases where you get periodicity, and here are the cases we get periodicity with inflation. So here we have sort of these base cases, and then we don't get anything new for a while. We're just going to get inflation going around for a while. So we start to think, well, maybe inflation is all we get. But then you get up to 327, and you get something new that doesn't come from inflation. Okay, we go on a little more. We get one more case at 4, and we keep going on to 500, and that's all we get. So we start to think we're probably going to run out. But we got to be honest about this, so we continue, and at 510, we get something new. And then we think, well, that really looks like the end of it, but we'll go up to 1,000 to be safe. not looking like anything new, but 978 is something new. So if we look at the examples not arising from inflation, you see we keep getting examples. They look rarer, but we keep getting examples. And so this leads us to conjecture that for any E, there are infinitely many values of n for which the best continued fraction expansion of the square root of E with numerator n is periodic, and in particular, periodic with period 1 or 2. And so the point of the rest of this talk is to prove this conjecture, and not only prove this conjecture, but show you how to obtain these values capital N. So that's what we're going to do. Okay, the first thing we're going to do is think about what happens with capital N small. Well, of course, for any value of E, there are only finitely many values of capital N small, but it's interesting to investigate that case here, and here we can answer the question exactly. If we ask when is the square root of E sub n periodic with period 1 or 2, the answer is that's true if and only if, when n is small, that's true if and only if A divides 2dn. And in that case, the expansion looks like this: d, 2dn over A, right, that's an integer, and 2d. And that's going to be periodic period of 2 if A is not equal to n. In that case, this will be different from that, but it's periodic at period 1 if A is equal to n, right? Okay. And the method of inflation tells us that if A divided 2d, then this would actually be an inflation of what happened from the CF1 expansion. So if A divides 2d and A is small, then we get simply inflation from CF1. But if A divides 2dn but not 2d, then we're going to get something new. Okay, so that was in fact the case here for square root of 19. 2d d is 4, 2d is 8. 3 doesn't divide 8, so we do get this by periodic at period 1. He's somebody new, not coming from the CF1 expansion. Okay, well that's the case. What happens when n is small? I say it's nice to have the answer, but that's not going to produce for us infinitely many values of n. So let's go to n large, and here's the next lemma that we have. Okay, suppose n is large, then we want to ask when is the best CFN expansion square root of E and periodic at period 1 or 2. Well, our theorem tells us that in the case of large, periodicity begins with A2. So if E sub n is going to be periodic with period 1 or 2, it's going to look like this. It's going to D here, it always starts with D. Here's A1, whatever it is, I'll call this R, and then starting, the period has to start with A2, so it has to look like PQ, 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 etc. So if it's going to be periodic, it's got to look like DR and then PQ with a bar N. And now you simply write down the equations for what it means to be periodic, and you find you get this system of Diophantine equations. Here it is, just look at this, and that's the answer. Well, the trouble is this system of Diophantine equations looks pretty useless, because if you look at it, this is cubic, right? My variables here are n, q, p, and r, right? And this is a cubic expression here. In fact, it's not even homogeneous. This is cubic, this bit is quadratic. We get two cubic Diophantine equations, which we have to solve. And solving cubic Diophantine equations doesn't look very promising. But we won't give up yet. The first thing we'll notice, though, is that this lemma tells us something interesting here. Because these two sides are equal, so that says that this is equal to this. Well, that says, so this is equal to this. We can cancel out an n here. A always divides 2AR, so we have to have A dividing 2DN. So we get a necessary condition. If the best CFN expansion of the square root of E is periodic at period 1 or 2, and n is large, then A must divide 2dn. So that's a necessary condition. In the case for n small, that was necessary and sufficient, but in case n is large, it's necessary but not sufficient. Okay, and as I say, there are lots of examples to show it's not sufficient. Well, as I said, this lemma doesn't look very useful, so we go to work on this lemma and we do some more algebra. And if we do some more algebra, we can cast this lemma in a much more useful form. Okay, first thing I'm going to need to introduce a little more notation here. So we had E is d squared plus A with 1 less than or equal to A less than or equal to 2D. we'll let B be the GCD of A and 2D, and B be A over G. So the two extreme cases where A divides 2D, then G is equal to A and B is equal to 1. And if A is relatively prime to 2D, then G is equal to 1 and B is equal to A, right? So these are the two extremes, but we could have something in between, okay? So, so it turns out if we do some algebra, what we find is we can reformulate this lemma as in the following form. Suppose we start with positive integer x and y, and we'll let capital W be x squared minus e times y squared, and capital X be 2ay minus 2d times capital N. And we'll let n be x minus capital D times y. Suppose we have two divisibility conditions. Suppose that n is divisible by b, right? This number b here, right? A over the GCD of A and 2D. Suppose that n is divisible by b, and that n times x is divisible by this number w. In that case, if we let r be equal to y, that's going to be integer. P be capital NX over capital W, that's an integer because of this divisibility condition. Q be capital X over A, that turns out to be an integer. In fact, it turns out to be this integer 2 times EY minus DX. Then if N is large, and these guys are large here, then the square root of E sub N is periodic period 2 with these coefficients. Right? With this value of N, X minus capital D times Y, and with these values of R, P, and Q. Okay, well, and I'll remark here that Q may or may not divide P, right? We get as soon as Q and P, there's not necessarily a relation between them. Well, okay, that's progress, but where are we going to get this guy W, and how are we going to ensure that N is divisible by B, and that NX is divisible by W, right? So this is progress, but it's still not so easy to use. So let's look at some special case of lemma 2.5, not quite as general, but still something that's easier to find out, okay? So here, let's suppose we look at x and y positive integers, and x squared minus e times y squared is b squared times capital V for some positive integer capital V dividing g. In other words, we're looking at this capital W, and I'm supposing I can write capital W as b squared times capital V, right, where b is this particular integer, right? B is A over G, right? A over the GCD of A and 2D. So suppose that x squared minus EY squared is B squared times capital V, and capital V, once again, there's got to be a condition on V, it's got to divide the GCD G, right? Okay, so we have this condition. Again, we're going to need the condition that x minus dy is divisible by B. Then for y sufficiently large, if we make these substitutions here, n is still x minus dy. That's what it was before here. N is still x minus dy. That's what it was in this preceding lemma. N is still x minus dy. But now r is y. Q is given by this. P is given by this here. These turn out to be all integers. P is also this multiple of Q, which turns out to be an integer. Then the square root of E sub n is once again periodic period 2, starting with A2 and with exactly these entries. Okay, so this is looking more promising, that we want x squared minus EY squared equals B squared times capital V. And I'll remark here that once I have something like this, I can do inflation, right? So I'm going to look at I can look at inflating here by some factor of m here to get really big values of n. Okay? Well, I'll just illustrate. I won't bother with this now. I'll just illustrate this later. So really, we're not so much interested in the inflation case, we're really interested in the base cases. So how am I going to get this to work? Well, here's right. I still have these conditions. I got to have x minus d times y divisible by b, and I have to have capital V dividing g. How am I going to get this to work? Well, the answer is I'm going to start to get this to work by using Pell's equation. So here's my next construction method, okay? Let's look at S and T positive integers with S squared minus E times T squared equal to 1, right? I know I have these. In fact, they're the solutions of Pell's equation. They come from the classical continued fraction expansion. Then for T sufficiently large, I get a continued fraction expansion, best continued fraction expansion of square root of E with numerator n in this way. And let's see what I'm going to do. I'll start with s squared minus e times t squared equal 1, and I'll simply let x be b times s and y be b times t. Well, if x is b times s and y is b times t, then certainly x squared minus e times y squared equals b squared. Okay? And my capital V is equal to 1. Well, now I'm in business here, because if n is x minus d times y here, right? And x is b times s and y is b times t, then n is b times s minus d times t. So n is certainly divisible by b. And v here, right? This is b squared times v. V is 1, so v certainly divides g. Right? V certainly divides g. So in this case, I can look at these solution s squared minus et squared equals 1, multiply x by b, y by b, and I simply get a solution here, right? And this tells me then I have infinitely many solutions, because I have infinitely many, I pick solutions in Pell's equation, I have infinitely many solutions to Pell's equation, I pick s and t to be solutions, x is b times s, y equals b times t, and I go to work, okay? So let me show you some numerical examples, and again, we'll start with 19, okay? So let's go equals 19, and we're going to start with examples that we get from Pell's equation, okay? So if we start with examples we get from Pell's equation, the first non-trivial solution of Pell's equation was x equals 170, y equals 39. Remember, I showed you this, this page with all the solutions way back up here. Let's see if I can find it again. Just be patient, we're getting there. Here we go. Right. The first non-trivial solution was p equals 170, q equals 39. The next non-trivial solution was p equals 57799, q equals 13260. So we'll get down to now where we are now. Okay, so our first solution is x equals 170, y equals 39. Okay, and if you simply put 170 and well, if you let s be 170 and t be 39, okay, b is 3 here, right? So e is 19, d is 4, a is 3, right? 19 is 4 squared plus 3. The GCD of a and 2d is 1. That's g, and b is a over the GCD, so b is 3 here, right? So we're going to look here, right? S is 170, y is 39, n is 3 times 170 minus 4 times 39. That turns out to be 42. And when you simply plug those numbers into my formula, you get the best continued fraction expansion of the square root of 19 with numerator 42 is 417, and then periodic with period 2, starting with A2 with entries 1708 and 122, and that's one of the ones I showed you in my preceding table. That was one of the values of n less than 100. Okay. That's the so that's the first solution we get from Pell's equation. Here's the next solution we get from Pell's equation. We can get 57799 for S, 13260 for T, and if you look at this formula for here in this corollary and you simply substitute, you find you get the continued fraction expansion, the best continued fraction expansion of the square root of 19 with this numerator 14277. Here it is with these rather large numbers here, but that's the answer. And then I can impress you by inflating this. I could take the 4759-fold inflation of this guy. I would get the best continued fraction expansion of square root of 19 with numerator 679,44243 would be this guy, period 1, starting at A2, and the best continued fraction of square root of 19 with 197436633, an even bigger number would be this guy, periodic at period 2, starting with A2, right? And one more base case, if I look at the the next solution for Pell's equation after the last one, 57799, 13260, that's going to be S is 19651490, T is 4508361, and you substitute here, you get a solution of Pell's equation with numerator, so a periodic best continued fraction expansion from this solution of Pell's equation with numerator 4854138, and here it is, a best continued fraction with starting at A2 with this numerator and period 2. Now, each one of these results is a little more special than the previous result. So let me give you one more example that comes from this theorem, which doesn't come from Pell's equation, right? So I wanted to look at, so here I'm going to look at B squared times V, right? So here, B is 3. So I'm going to once again try to look for something where V is 1, so I don't have to worry about divisibility. I will have to worry about divisibility by B here, but let's take B equals 3. So I'm looking at B squared, which is 9, okay? So I'm going to look here for a solution of, sorry, went past this here. I'm going to look at a solution of x squared minus 19y squared equals 9, okay? And it turns out that that's a solution. X has a solution, x equals 11878 and y equals 2725. And these two numbers, 11878 and 2725, are not divisible by 3. But x minus d times y, which is 978, is divisible by 3. So I get a solution, square root of 978 is 4, and then numerator 978, period 2, starting with A2, and that's the last example that I gave you for less than 1,000. So if we look at the periodic list for less than 1,000, and we look at period 1 or 2, then it turns out that here's where the solutions come about. Here's this one coming from Pell's equation, this one from the last parallel before Pell's equation, and then these other ones that come from Pell's equation give you ones with much bigger numerators. Here, I say the next one giving you 14277. But in any case, we get infinitely many of these examples, and that's what I wanted to show you. So I will end here, and thank you all for your attention.
Oh, thank you very much, Steve. Wow, I wonder, probably had a lot of trouble preparing the slides.
No, it's par for the course, So.
Okay, so there is a delay between the transmission and the YouTube. So it takes some time until we get the questions from the audience.
Okay.
I have a question myself. So when I think about continuous fractions, I think about the work of Ramanujan. And can you tell us a bit about the history of the continuous fractions problems and the closed forms?
Yes. So there are actually two different aspects to the theory of continuous fractions. One is the arithmetic aspect, and that's what I've talked about. The other is the analytic aspect. Right, continued fraction expansions of functions. That's a whole nother theory. It's quite a different theory, right? That's asking analytic questions rather than number theoretic questions. And that's the end of continued fractions that Ramanujan worked on. So this is Ramanujan did related to what I've been talking about.
And so. This is not a very common theme when you think about algebra courses. How did you come up with this idea for coming to talk about this theme today?
Well, as I say, it's not a common theme in algebra courses, but classical continued fractions were important in number theory precisely. I say there are many reasons for them. People have been investigating them for a long time, but one of the places they come up is in solution to Pell's equation. I'm not saying Pell's equation is what we in the West call it. This was, and in fact, it's a misnomer. It's a well-known misnomer. Pell had really nothing to do with this equation, but Euler thought he did. So Euler called it Pell's equation, and the name is stuck. This equation was considered by Fermat before Pell, and Fermat used infinite solutions. But way before Fermat, it was considered by Indian mathematicians. even a millennium before Fermat. So this actually goes back a long way. So the answer was that I was thinking about one of my interests is number theory, and I was thinking about some reason Pell's equation popped into my mind, and I started thinking about continued fractions. And I remember I was on sabbatical in Germany. I was sitting in my office in Göttingen, and I said to myself, what happens if you change 1 to n? That just seemed to be a very natural question. And I said, oh, well, that's such a natural question. People must have been thinking about it. People have been thinking about continued fractions for centuries. People must have been thinking about this for a long time.
Oh, I see.
I discovered that people hadn't been thinking about this for a long time, and in fact, people had hardly been thinking about this at all. So these basic results about continued fractions are really new results. And as I say, there's this conjecture that they're not always periodic, right? I think that's a great conjecture. I wish I knew how to prove it. I think that's a great thing for somebody to work on. I must admit I have no idea how to prove it, right? So I was happy to be able to prove that there are infinitely many cases where it is periodic, right? So I know there are infinitely many cases where it is periodic, and I suspect that there are infinitely many cases where it's not, but I can't prove that. So, give a lecture, hope to inspire a new generation of mathematicians to do new mathematics. So here's a challenge to my audience. Take up the baton where I've left it here and go to work.
Okay, thank you very much. I just, one question from the audience just arrived. I put it on the screen for you. Can you see that?
Well, you're asking me a question, and the answer is I haven't thought about that, right? Maybe, maybe, I don't know.
Okay. So this is the only one so far. So what is the state of the art? What are still the interesting points being investigated in this area of continuous fraction? But this is something that you don't see very much in the literature. Well,
mathematics is a kind of specialized business, and there is a specialized literature about continued fraction. I'll tell you a bunch of other results. So it's known that the classical continued fraction, you can have expansions that are arbitrarily long. I mentioned that you look at a periodic irrationality, you can have expansions that are arbitrarily long. I strongly suspect that the same thing is true for numerator n. But again, I don't know how to prove that, because you can't just start off with some periodic irrationality and say, oh, you pick one which has a
oops. Oops, there is something wrong here.
Okay, back again. Right. So I suspect that you can get periodic best expansions with period n that are arbitrarily long. I don't know that. I'll tell you another thing. So I told you that the ones that are have this palindromic pattern are almost all the time, but not all the time. In fact, I said we did lots of examples, and I know exactly 2 examples where it doesn't have this sort of palindromic behavior. If you look at the continued fraction expansion of the square root of 31 with numerator 13, and you look at the best expansion, that's got period 4, periodic starting with A2, as our theorem says it must be, but it doesn't have this palindromic behavior. And if you look at the square root of 87, the best continued fraction expansion with numerator 58, that's got period 6, but it doesn't have this palindromic behavior. And those are the only examples where either E is less than or equal to 200 or N is less than or equal to 200. So this is a very rare phenomenon, right? I say it's good we did so many examples, but it's a very rare phenomenon. So it might be nice to know that well, numerical evidence indicates it's very rare. It might be nice to know that it really is very rare, right? That almost all the time you get something that's palindromic. Also, another thing is that even in the classical case, it turns out that odd periods are much rarer than even periods. And how about the case where n is bigger than 1? I suspect the same phenomena holds. In fact, numerical evidence says that odd periods are extremely rare. So once again, I have lots of numerical evidence, but not so many theorems. So I think that there's a lot of room for people to investigate what's happening here. As I say, there really aren't so many people that have investigated this. So this really is unplowed territory for people to work on. So I'm going to give this talk because I think it's, well, I'm biased. I think it's beautiful mathematics. I hope that you think so too, but I'd like to advertise this subject. I'd love to have somebody make more progress. And as I say, I think this is a great conjecture that the best CFN expansion is not always periodic. And I think that's sort of the main conjecture that I have in this subject. And I would love to see somebody prove it. But I can't even give you a hint. I have no idea how to do it.
Oh, thank you very much. We have a lot of algebra students here in our department. I think they will think your talk is very inspiring, and it's very, very interesting. I'm not from this area, but the problems that you pointed out today, they were really very challenging. So thank you very much.
Before I go, let me give you two references, actually. Okay. So the first paper that Max Anselm and I wrote about generalized continued fractions is in the Journal of Number Theory. I don't remember the exact reference, but if you get the journal, you can look it up. And then this result about periodicity of generalized continued fractions, that appeared in the journal Monatshefte für Mathematik. So again, these are listed on MassSciNet, so you can find them on MassSciNet, but that's a hint where to go. Okay, but thank you again for the talk. I enjoyed doing it, and I hope your audience enjoyed hearing it as much as I enjoyed giving it.
Okay, Steve, thank you. It was really a pleasure here in our colloquium this Friday. So thank you very much for delivering the talk and for accepting the invitation. It was really very amazing. Thank you very much. So some final words to our students. Do you have some final words to our students?
Those were my final words. So, I enjoyed giving the talk, and I hope you all enjoyed hearing it as well.
Ok, so let me say farewell. Bom, boa tarde a todos. Então, nós nos encontramos na próxima sexta-feira para a próxima palestra, às 14 horas. Muito obrigado pela participação de todos e uma boa tarde.